All right, well then let's get started here so we can get to that wonderful word problem. Today we are going to be looking at systems of linear equations. And I have a nice Charlie Brown cartoon just because I thought it was kind of cute how he's blowing up the balloon but only halfway. There's our joke. Any LOLs out there would be wonderful because, you know, math jokes are always cheesy. Hey, Katie, good to see you in here. Anyways, it comes down to the idea of how we're going to be reading and looking at mathematics and how we're going to interpret it. And this Module 5 is very heavy with word problems. And I know most of the students I work with, you know, word problems have always been difficult. So today I'm going to try to help you conceptualize and understand a little bit more about word problems. And we're going to do that through the method of systems of linear equations. And so a system of linear equations is when we have two and sometimes more, but in this unit we're only going to be working with two linear equations. And we just worked with linear equations in Module 4, where we're looking at a line, it's got a slope, it's got a y-intercept. So we're going to be looking at two of those lines, and we're going to be trying to figure out if it has an intersection point, and if so, where is it? We're going to look at this in kind of three different ways. There are more ways to look at systems of linear equations, more methodologies, but I'm going to focus this in on three types. And really the main one we're going to be looking at is substitution. So first, let's discuss a little bit more about systems of linear equations and how many solutions they have. So we need to go back again and think about our understanding of lines. And lines, the main idea that we're going to be using is that these systems of linear equations have one solution. Okay, it's kind of in yellow. I know it's hard to see down here, but we're looking at where these intersecting lines have one solution. And those lines, they don't necessarily have to be perpendicular. These ones look perpendicular. But in general, as long as the slopes are different, we're going to have some sort of intersection point. However, systems of linear equations could have what we call infinitely many solutions. And this is going to occur when we have two lines that are exactly the same. You can kind of see we've drawn a blue line and behind it the green line. This is where we have two lines exactly the same. We're going to be looking at something, we're going to call the number of solutions infinitely many solutions. Now note, something really important to realize is we do not say that it has all solutions, okay, or every point is a solution. Okay, can any of you think, why is it not correct to say that every point is a solution or that all points are a solution? Why would we not say that all points are a solution? Good. So French said that not all points, because that would refer to points not on the line. Exactly. So we say we have infinitely many because this line goes in, you know, infinite direction, you know, both to the left and to the right. But we can't say that all solutions, all points are solutions, because that would mean that point floating out there would be a solution. So we have infinitely many solutions or infinitely many solutions on the line. The last option for the number of solutions is parallel lines. Okay, and parallel lines we know have the same slope, but have different y-intercepts. And because of that, we can think about those two lines going on and on and on forever, and they're never going to intersect. Okay, in a two-dimensional world, those lines are never going to intersect. So the three types of solutions we could get is one solution with intersecting lines. Okay. That's what we'll mainly be working with, but I don't want to disclude the idea that we could have infinitely many solutions or no solutions. So let's take a closer look at that then. I'm going to set a poll up for us here. Okay. So I want you to kind of think about how many solutions does the following system of linear equations have? So I've given you two lines here. And through whatever method you want, I want you to think about how could I figure out how many solutions this system has. And once you've kind of thought about that, worked it out, I want you to go ahead and poll in using A, B, or C. And remember, your poll button is above where we see the chat in the main room. You have your smiley face, which gives you your different emoticons. The little person with the clock that tells you we're away, hand raising, or the button that has an A in it. And if you click on that, you can see A, B, C, and you're able to poll in. Okay. So you've learned about lines, and I just kind of want you to think through now, how many solutions is this system of linear equations going to have? Again, I'll give you a little time to work and think about it. Think about what I just showed you, some graphs. How could you maybe graph these or solve these so you could figure out how many solutions it has? Okay, I'm going to give you another 15 seconds. I know you might not be done, but I'm going to close the poll. So kind of final thoughts, go ahead and just check something if you're not sure. Okay, well, let's see what you came up with. Good, half of you were able to poll in and came up with the idea of C, and some people just weren't quite sure. And that's okay. I just wanted to see what people were thinking. So for those of you who did poll in and you did understand and get C, what methods did you use to figure it out? I'm just curious. Go ahead and type in the chat. What method did you use to solve this? Okay, so there's multiple methods. I'm just curious what you did. Okay, one person put the line in standard form. Okay, what else did you do? Okay, Kay solved the second equation for a y equals. Good. Wendy did a similar thing, solved the second equation for y equals. Either of them is going to get you to the same idea. So I also like to solve things in y equals mx plus b because that slope-intercept form is very nice for me to work with. So if I wanted to solve the second equation for y equals mx plus b, I would start by subtracting 4x on both sides. And after I've subtracted that 4x on both sides, I need to divide both sides by a -6. And this will lead me to y equals a positive 2/3 x minus 4. And so we can see that they are exactly the same line then. 1 and 2 are exactly the same line. And remember, we said when we have exactly the same line, we would have infinitely many solutions. But let's take an even closer look now at solving. So we did some algebraic manipulations. A couple other ways we can look at this is graphing and t-charting. So here I have two lines, and these lines aren't the same. So let's start by doing a little t-chart, okay? And we'll say that the green t-chart will be number one, and the yellow t-chart will be for the second equation. So for the first equation, I like to solve these for y equals mx plus b. So y equals a negative x plus 3. And that's what I'm going to use in my t-chart here. And the way that I use a t-chart is I know that I want to look at some points right around the origin. So I usually start with 0. And I know I put 0 kind of in the middle because I'm also going to want to see what happens at 1 and 2, and maybe also at -1 and -2. So that means I'm going to take my points for x, plug them in here, and figure out what my y values are. And so I can see a negative times a -2 is a positive 2 plus 3 is 5. Negative times a -1 is a positive 1 plus 3 is 4. 0 plus 3 is 3, and I can see because I have a slope of a -1, my y values keep decreasing by 1. Okay, so there's a t-chart for the first equation. And while we're at it, we might as well graph that. So I have 0, 3 as a point, 1, 2 as a point, 2, 1 as a point, and I can go ahead and connect those lines. Something like that would be our line. Okay. Now we will work with our second equation. So I have x minus y equals 1, which if I want to rearrange this, I would subtract x from both sides, getting y equals a negative x plus 1. So then I'd multiply everything by -1 to get y equals a positive x minus 1. And again, I like to see what happens right around the origin. Okay. So I'm again going to fill in my t-chart. I'll have a -2 minus 1 is a -3. -1 minus 1 is a -2. 0 minus 1 is a -1. And again, I can see I have a positive slope of 1, so my y values continue to increase by 1. And I can plot those points, 0, -1, 1, 0, 2, 1, and fill that in with a line. And what this allows us to do is find that intersection point. Through the t-chart, we can see that the point 2, 1 was listed both times in that t-chart. So we know that that is the intersection point. We can also see this graphically. Okay, that the point 2, 1 is the intersection point. But when is graphing and t-charting not going to help us? Well, the t-chart, I chose points, just 5 points, very close to the origin. But that might not be helpful if our intersection point was perhaps 117. Okay? We probably wouldn't continue t-charting around the origin out to 100. That would be, a rather long t-chart. I wouldn't want to deal with that. Graphing is nice, though. It can kind of help give us an idea. But what if my intersection point is 1 3/4, -2 5/8? Okay? Something like this. Maybe right there. Hard to tell. It's going to be hard to tell exactly what that is. So graphing and T-charting are great. They can give us a nice overview of what our lines might look like, where we might find an intersection point, but it does have its limitations, which is why I really like to use the idea of substitution. So I'm again going to be using this same set of lines, x plus y equals 3 and x minus y equals 1. I'm going to solve for y equals in the first equation. Okay, and we're going to look at how we choose variables to solve for in a little bit. But the idea of substitution now is I'm going to take these two lines. I'm going to solve for one of these variables, and I'm going to substitute it into the other equation. Okay, so we're going to do kind of a quick overview, and then we're going to slow it down and practice it. So again, my first step is to solve for one variable, which I have done. I've rewritten my two equations. Notice that this first equation, I've rewritten it as the equation that I solved in step 1. I'm now going to take that equation that I solved for, and I'm going to say that y equals a negative x plus 3. I'm going to substitute that in for y in my second equation. And the reason is, if I'm looking for this intersection point, then I know that the y variables have to be the same in both points. I also know that the x variables have to be the same in both equations. So it's not going to matter which variable I solve for because I am looking for this intersection point. And you can see here the substitution occurred right here. So I originally had x minus y equals 1, but I said since y equals a negative x plus 3, again I had re-solved that equation in the first step, I'm going to substitute that in, okay, or plug it into the second equation. Now I'm going to continue with the algebra. Okay, I'm distributing the negatives to get x plus x minus 3 equals 1. X plus x is 2x, and minus 3 equals 1. I add 3 to both sides and divide by 2. I find that my x equals 2. And this is just the algebra that we will continue with once we have substituted in. And the reason we do that substitution is so that this whole equation is now written in one variable. We can solve equations once it's written in one variable. And again, these were the same lines that we used previously, and we know that x equals 2 from graphing and T-charting was the variable that we were looking for. And then the last step is to plug our solution back in. So we found that x equals 2. Again, we have these two equations. It doesn't matter which equation you substitute 2 in for, you will find the same solution. So here I said x equals 2. I'm going to substitute that into the first equation to get y equals a negative 2 plus 3, which is 1. I could also take and substitute that in here. 2 minus y equals 1. And I can see that y would have to equal 1 as well. So the substitution, making sure it works in both equations, is really critical. So then we know our solution is the point 2, 1. Okay, remember that is a point. If we were to graph it, which we did earlier, that's a point. So we write it, as an x comma y. Okay, that's substitution in a nutshell. So now I want us to practice, but before we practice, I want to talk a little bit more about this idea of which variable you want to solve for and in which equation. So let me set up the poll. So we have A through D going on here. All right, so I want you to think about just looking at these two equations, 4x plus y equals 3, our first equation, and 3x plus 5y equals 15. Which variable is going to be easiest to solve for, and in which equation? So are you going to be looking at x in the first equation, y in the first equation, x in the second equation, or y in the second equation? Which variable is going to make the most sense to solve for? Okay, good. I'm going to publish our poll here. Okay. Good. Most of you looked at B, which was y in the first equation. And that's probably what I would choose, because we can see that we would subtract 4x to get y equals a negative 4x plus 3. That's pretty easy to look at. Let's look at D though, y in the second equation. If we solved for that, we would start by subtracting 3x. I'm going to do that work up here. So we would have 5y equals negative 3x plus 15. Then we'd have to divide everything by 5, okay? Which means we get y equals a negative 3/5 x plus 5. Now, that's not terrible to work with. It just might not be the easiest. We're always going to look for the easiest variable to make our substitution work. Okay? Good. So I wanted to point that out, and now I want you to practice. See if you can't figure out what the solution is. What is our intersection point? Whatever way you want to solve this, graphing, T-chart, or substitution, go ahead and solve this system of linear equations. Okay, as you continue to work, if you do get an answer, go ahead and type in. Wendy got 0.3. Can anyone confirm or let her know if maybe you got a different answer? All right, Kay seems to have gotten the same answer. French got the same answer. Okay, for those of you who still might be working, I'll start talking through how I found a solution to this. And I did find the solution 0.3. So let's take a little closer look at this. I have already solved one of my equations, my first equation here, for one variable, y equals a negative 4x plus 3. I'm going to take this negative 4x plus 3 and substitute it into the second equation. Note how I take from one equation and I substitute into the other. So I get 3x plus 5 times the quantity, negative 4x plus 3 equals 15. Okay, and now distributing 5, I get 3x minus, it's minus sign, minus 20x plus 15 equals 15. And in subtracting 15 on both sides and combining like terms, I get a negative 17x equals 0. And well, if negative 17 times something equals 0, we can see then that x has to equal 0. Okay, and x equals 0 is totally a valid point. I then took x equals 0 and said, well, if y equals negative 4x plus 3, then y has to equal negative 4 times 0 plus 3, which means y equals 3. So my point is 0, 3. I could have also graphed this and noticed that it is the y-intercept. I also could have written 3x plus 5y equals 15. Oops, I did that wrong up above. Someone didn't say anything. Well, when I solved that second equation up above, I saw y equals negative 3/5 x plus 3. I could have noticed that it is the y-intercept in both cases. Nice job. So that's a little bit about substitution. And there's also a strategy called elimination. It's not one that I use often, but some of you may have heard it, may have seen it. So just so you know that there's other methods out there, but we're mainly going to use substitution. And now we're going to move on to everybody's favorite, word problems, our wonderful application problems. We love Calvin and Hobbes. They always have some good math cartoons. Point A is twice as far from point C as point B is from point A. If the distance from point B is to point C is 5 inches, how far is point A from point C? And he gets kind of freaked out, and he says, the living dead don't need to solve word problems. No, we might not need to solve word problems, but in actuality, these are the problems that are most applicable, that can actually help us model everyday life. So I like to look at them. These are some steps. I think often in mathematics, sometimes, especially in word problems, we don't have a system, a way to attack them. So these are kind of my steps that I will continually go through as I work through word problems. First is just reading the problem. Okay, that's like a big duh, right? We know we need to start by reading the problem. The second step is to define the variables. And in systems, as you've seen, we have x plus y, or x and y. We're going to have two variables. We might not always call them x and y, but we are going to have these two variables, and we're going to have two equations. And I think steps 2 and 3 are the hardest. Trying to figure out what are our variables, what's changing in here, and how do we create these equations. Because once we figure out what the variables are, and once we figure out what our two equations are, then we're using algebra. We're using our idea of substitution, which we just looked at, or again, graphing or t-charting or elimination, and to solve the problem. And then we have to make sure that we state the answer to the problem and label. Okay, whether we're in feet or inches or miles per hour or ounces, we need to make sure that we label these problems. So if you ever get stuck, these are my steps for looking at a word problem. Read the problem, and especially 2 and 3 here. Define those variables and create two equations with those two variables. So we like money. We always seem to have money problems. So one morning I went to Murphy's Mug, the little coffee shop here at UW-La Crosse. And I bought a 14-ounce hot chocolate and 3 slices of pumpkin bread, and it cost me $3.75. The next morning, my friend and I bought 2 14-ounce hot chocolates and 4 slices of pumpkin bread, and it cost us $6. So we want to figure out how much will I pay to buy 1 14-ounce hot chocolate and 1 slice of pumpkin bread. Okay, so we've read the problem. If you're like me, I like to underline key ideas here. So at the end, I underlined what I'm looking for. How much am I going to pay for 1 14-ounce hot chocolate, 1 slice of pumpkin bread? I might also look at the idea that I bought a 14-ounce hot chocolate and 3 slices of pumpkin bread. I bought 2 hot chocolates and 4 slices of pumpkin bread, and it cost me $6. So first we need to figure out what our variables are. What is changing, okay? Or what are we trying to figure out? What don't we know, and what are we trying to figure out? Any ideas? Go ahead and type in if you think about it. When we're looking at our variables, Okay. What don't we know? What are we trying to figure out? That's the question to ask with variables. Any ideas here? Awesome. Thanks, Katie. So we're looking at the cost of a hot chocolate and the cost of pumpkin bread. So I'm going to go with H equals the cost of one hot chocolate. And if you want to use X and Y, that's fine. But I sometimes like to use the letters that are represented in the equation. So then I'm going to say P is the cost of one pumpkin bread. Okay, so it's not the number of each of them. We happen to know the number of each of them. It's the cost. That's what we don't know. So now we have our two variables. We want to look for two equations. Okay, and our two equations are kind of set up for us nicely in this. I went and I bought a 14-ounce hot chocolate, which contains one hot chocolate, and 3 slices of pumpkin bread, and it cost me $3.75. Well, that means if I'm looking at cost, I'm looking at the cost of one hot chocolate, and I don't need to put a 1 in front of it, it's implied. One hot chocolate and 3 slices of pumpkin bread. And so the cost of the hot chocolate and the cost of 3 slices of pumpkin bread is $3.75. Okay. So I've given you that first equation. See if you can't model the second equation and type it in for me. Okay. So now that I've kind of helped you with that first equation, what might that second equation look like? Thanks, Katie. So we've got 2 hot chocolates, which you got from right here. And we have 4 slices of pumpkin bread. And the total cost is $6. Okay? To me, that's the hardest part. Coming up with my variables and coming up with my 2 equations. Now that I have these 2 equations, I'm going to use the idea of substitution and solving. And so for me, what's easiest to solve for is H in the first equation. I'm not saying it's the only way to solve. H in the second equation isn't bad to solve for either. But see if you can't figure out then what we're going to find for the cost of a hot chocolate and the cost of a pumpkin bread. All right, Katie's on top of it. 225. Let's see where she got that. I'm going to say that H equals 375 minus 3p. I've rewritten my first equation in terms of H by subtracting 3p over. I'm now going to take that and substitute that in for H in the second equation. Good, French agreed with that. So I have 2 times 375 minus 3p and I'm adding to that 4p, and the total is still $6. So now using algebra, I'm going to distribute 2 to 375, giving 750, I believe. Yeah, 750 minus 6p plus 4p equals $6. A negative 6p plus 4p is a negative 2p. And if I subtract 750 on both sides here, I get a negative 2p equals a negative $1.50, which which seems weird, but once we divide by that negative, we see that the cost of a pumpkin bread is 75 cents. Okay, so then we can take that cost, pumpkin bread of 75 cents, and bring that back in to figure out that 375 minus 3 times 75 cents is $1.50. So the hot chocolate equals $1.50. Again, what I did here is I just plugged in or substituted in 75 cents for the cost of the pumpkin bread. So I figured out that the hot chocolate is $1.50, but what I was really asking was how much am I going to pay to buy one hot chocolate and one slice of pumpkin bread. So that's where we're getting $1.50 plus 75 cents to figure out $2.25. Okay. Nice work. So that's kind of a traditional word problem, but now we have some word problems that I think are a little trickier. And before we started, someone was asking about this idea, mixture. So I'm going to take a little time to talk about these mixture problems. So a mixture problem might read something like this. I have a 6% sugar water solution. And sometimes instead of sugar water, I'll say something like I have a 6% sugar water Kool-Aid, right? You can think of it as Kool-Aid, Kool-Aid, sugar, and water. And an 18% sugar water solution. How much of each solution do I need in order to make 750 milliliters of a 10% sugar water solution? Okay? And so first I want to kind of just visualize what this is even asking for. In my mind, I can see kind of two buckets. All right, I have something and another something, right? The 6% sugar water and the 18% sugar water. I'm going to pour those together to get this third solution, all right? But sometimes it's kind of weird because you think you're taking a 6% and 18% and getting 10. Well, 6 minus 18 or 18 minus 6 isn't 10, and 6 plus 18 isn't 10. So what's going on? Sometimes I like to equate this to the idea of paint. All right? Let's say our 6% sugar water solution is a really light blue Kool-Aid. Okay? Let's say instead of sugar, it's that kind of blue powdery stuff that you get in Kool-Aid. So if I have a 6%, it doesn't have that much blue with it. But if I have an 18% solution, we're going to get a lot of blue, right? Again, I'm just making it up that this is actually blue Kool-Aid, okay? So 6%, sometimes I like to call this my weak solution. And then 18%, sometimes I like to call this my strong solution. So I'm taking a weak solution and a strong solution, and when I mix these together, as you can see kind of on this paint strip, I'm going to get something in between that lightness, right? I'm going to get something like this 10% here. Okay? That's kind of my way of visualizing kind of what's going on in these mixture problems. All right, I'm going to take a weak solution and a strong solution. I'm going to mix them together to get something in between, right? I can't get any stronger than 18%. I can't get any weaker than 6%. I'm going to get something in between. All right, so I use something kind of called the bucket method. Okay, and in the bucket method, again, I'm going to start by defining my variables. What don't I know? Well, I don't know how much of the 6% sugar water solution I need and how much of the 18% sugar water solution. So I'm going to call X the amount, and the amount is going to be in milliliters. Okay, I'm going to have some amount of sugar water solution, and I'll say this is the amount of the 6% sugar water solution. And then y is going to be the amount, again in milliliters, of my 18% sugar water solution. Okay. Again, I'm going to think about these in terms of buckets. Think of it as Kool-Aid. You've got one Kool-Aid that only has 6% sugar, another Kool-Aid that got a little sugary and has 18%. And you kind of want to mix them together to get something in the middle. Right? So here's my buckets. They're full of Kool-Aid. And now I'm going to kind of fill in what I know and what I don't know. I know what my outcome is. I know that I want this to be 10% of 750 milliliters. Okay. I also know that I want to use 6% sugar water solution and 18% sugar water solution, but I don't know how much of the 6% or how much of the 18% that I need. Okay? And so this bucket idea here tells me I've got 6% of so many X milliliters, 18% of Y milliliters, and I want to get 10% of 750 milliliters. This leads me into my two equations. My first equation is just looking at the number of milliliters. I don't know how many of X or how many of Y, but in total I want 750 milliliters. Okay, so I don't know the amount of each of them. Maybe it's 200 and 550. Maybe it's 300 and 450. I don't know what it's going to be, but adding them together, I should get 750 milliliters. The next equation is looking at the concentration, the actual amount of sugar in the sugar water. So this is telling me then that I have 6% of X number of milliliters is sugar. Okay, I'm just looking at the concentration part now. 6% of that X milliliters is sugar. And notice 6% is written as 0.06. Be very careful not to write 6% as 0.6, which looks like 60%. Okay. Then I'm going to be adding to that 18% of Y milliliters. Okay, that's the number, that's the amount of sugar in the second bucket. And in total, I want 10% of that 750 milliliters to be sugar. Okay. I know that's kind of a longish explanation, but I'm hoping that makes sense. The idea that I have some amount, X of milliliters of 6% and some amount of Y milliliters, and I'm getting 750 total milliliters. That's just looking at the milliliters part. Then the next part looks at the sugar concentration. And now that we have those two equations, we can substitute and solve. So just looking at those equations, are there any questions with that that I can answer? If not, go ahead and continue working, see if you can't figure out how much of each solution that I need. Okay, any questions on that setup? Okay, then go ahead, let's work through it. And I'd start by solving y equals 750 minus x. You could say that x equals 750 minus y. Doesn't matter which way you want to do that, but I'm going to take that and I'm going to substitute that in for our y variable in the next equation. And if you've figured it out, go ahead and type that in. I'm just going to kind of keep working through the math so that you can keep either following me or figuring it out on your own. Right now I'm distributing my 18%. Well, looks like French figured something out. Let's see if we all can't get to that same part. Combining my like terms. Okay, looks like I'm getting the same thing. I'm figuring out that x equals 500. And if I look back to how I defined x, so that was the amount of 6%, so I get 500 milliliters of my 6%. And if I know in total that I wanted 750 milliliters, that means that y has to equal 250 milliliters of the 18% solution. I also could have figured out that by saying y equals 750 minus x and substituting 500 in to get 750 minus 500 is 250. Nice job, nice work. So that's just kind of a little overview of systems of linear equations. We did kind of 2 word problems, this mixture word problem, which I think is not too difficult once you're able to kind of conceptually understand what's going on. Now there's variations to these, such as adding pure water. If I'm adding pure water, here's just a quick question for you. If I'm adding pure water to something, and I'm talking about a sugar-water solution, what percent concentration is pure water? Go ahead and type it in. What percent concentration is pure water? Okay, good. The percent is 0. The idea is if I have pure water, good. I have nothing, right? No sugar water. Versus if I'm adding pure sugar, okay, if I'm adding pure sugar, then I've got, yep, 100%. Okay, so those are some variations that I could be adding pure water, kind of diluting it down, right? Or I could be adding pure sugar, which would be, you know, really increasing that amount of sugar. So that's kind of what I have for you today. Now there are a lot more types of word problems, and it would take a long time to go through all of them. So I really encourage you to get into those learning objects, work on them. But in general, I'll go back to kind of my steps. What we've done is we always read that problem and then define the variables, really trying to figure out what it is that we don't know. What are we trying to solve? And then after we define those variables, create those 2 equations. And those 2 equations, you know, almost always have 2 variables in it. Then use that idea of substitution, solve, and labeling. So good. I'll stick around for another 5 or so minutes if anyone has any questions. Otherwise, thank you so much for coming and participating in today's live lecture. And I hope that everything in your MOOC journey has gone well.
Maggie?
Yes.
I would just add one thing in terms of reading the problem, read the problem several times. I think so often math students expect to read the problem once, like you would a true-false question on a social studies test, and be ready to go. And it takes a lot more than that to really understand what the problem is all about. So read it many times.
Yeah, absolutely. Kay is one of our fabulous online tutors. So again, she's a great person to go to. But you can see that we went through and I was underlining things. I was referring back to those to that word problem several times to make sure that I understood. I even had to you know, in this case, kind of talk through conceptually what's going on. So good. Thank you for that input, Kay. Wendy, good. I'm glad that the live lecture today answered your question about the self-check. And again, anytime you have questions, that online office hours is a great time. You don't have to go for the full hour. You can just pop in for 5, 10, 15 minutes to get those questions answered. So thanks so much for coming.